welcome to Lecture 26, 6.2, the binomial probability distribution. So for Objective 1, we're going to determine whether a probability experiment is a binomial experiment. Alright, so the criteria for a binomial probability experiment. First off, an experiment is performed a fixed number of times. And then each repetition of the experiment is called a trial. The trials are independent. This means that the outcome of one trial will not affect the outcome of the other trial. For each trial, there are two mutually exclusive or disjoint outcomes, which are success or failure. And the probability of success is the same for each trial of the experiment. Okay, so some of the notation used in the binomial probability distribution. So there are n independent trials of the experiment, which would be the lowercase n. And then we would let p, lowercase p, denote the probability of success for each trial. So that 1 minus p is the probability of failure for each trial. And then we'll let capital X denote the number of successes in n independent trials of the experiment. So x is greater than 0 and less than n. Example 1. Determine which of the following probability experiments qualify as binomial experiments. For those that are binomial experiments, identify the number of trials, probability of success, probability of failure, and the possible values for the random variable x. So for the first one, a probability experiment in which 4 cards are drawn from a deck with replacement and the number of hearts is recorded. Alright, so the first thing we're trying to see is if this is performed a fixed number of times. And yes, so for 1, it is performed a fixed number of times. Next thing we're going to check is that the trials are independent of one another. So let's see. So we pick cards and then, we are doing replacement. Okay. So because we're doing replacement, the trials are going to be independent of one another because we reset the deck each time. So this would be trials are independent. And then 3. The next thing we're going to check is that there are only 2 possible outcomes of the experiment. So what are the 2 possible outcomes? Well, the first outcome is we get a heart, and then the other outcome is we don't get a heart. So we either pick a heart or not, which would be success or failure. And then lastly, we're going to check. So the probability of success for each trial is constant. Let's see. Well, the probability of success for this, now we're talking about hearts. So how many possible hearts are there in a deck? Well, there are 13 cards per suit, and we have 52 cards in a deck. So the probability of picking a heart would be 13 out of 52, which is going to be the same each time we do the probability, or each time we do the trial, because we are doing replacement. Okay, so it satisfies all the 4 criteria for being a binomial experiment. So what would be the probability of success? So 13 over 52 would be the probability of success. Then what would the probability of failure be? Well, probability of failure, so I'm going to go ahead and write this down here. Probability would be 1 minus 13 over 52. So what would 1 minus 13 over 52 be? That would be, so 15 minus 13, that would be 39. So probability of failure would be 39 over 52. Those are the remaining cards in the deck that are not hearts. And lastly, we need to find the possible values of the random variable x. So the possible values of the random variable x are going to be the number of hearts chosen which is either 0 hearts, 1 heart, 2, 3, or 4 hearts chosen, because that's the number of times we are doing this experiment. Now, let's take a look at B, a probability experiment in which 4 cards are drawn from a deck without replacement and the number of hearts is recorded. Let's go ahead and follow the same criteria we're looking at. So first, it is the experiment performed a fixed number of times? The answer is yes, it's performed 4 times. So the experiment is performed, yeah, that's ugly performed a fixed number of times. Second, are the trials independent? Well, let's see. So if I pick 1 card from the deck, the probability of that being a heart is 13 out of 52. But I'm not doing replacement. So 1 card is missing from the deck when I try to pick the second card, which means that the probability of picking a heart from that deck might be 13 out of, well, 1 card's missing, so 51, depending on if that was a heart or not, or it would be 12 out of 51, once again, depending on whether or not that one was a heart. So the probability is not the same for success each time. Because remember, we need to have the same probability of success each time. So this does not pass the rules for binomial experiment. So we will go ahead and write down, well, one of the ones that didn't pass was the trials are not independent. All right, and then let's see, our answer would be this is not a binomial experiment. Because it does not satisfy the criteria. Now let's take a look at C. An Olympic archer who historically hits the bullseye 83% of the time is asked to shoot 4 times, and the number of bullseyes are recorded. All right, so the first thing we're looking at is, are the experiments performed a fixed number of times? And the answer is yes. Once again, it's 4 times. So a fixed 4 times, 4 experiments. Number 2, are the trials independent? Well, let's see. They are, because the probability of shooting the first time is not going to affect the probability of her shooting the second time. So the trials are independent. And 3, let's check. So, are there only 2 possible outcomes? Yeah, there are only 2 possible outcomes. Either you get a bullseye or you don't. There are 2 possible outcomes. Bullseye or not. And then lastly, the probability of success for each trial is constant. And this would be yes, the probability of success is 83%, which we got from the problem, which means the probability of failure is 17%. Okay, so this is a binomial experiment. It satisfies all the criteria. So this is a binomial experiment. Sort of running out of room here. The last thing we need to do is to write out our x values. So our x values are going to be, let's see, either there's 0 bullseyes, 1, 2, 3, or 4 bullseyes. And there we go. The work was really cluttered, so I went ahead and boxed my work. All right, objective 2, compute probabilities of binomial experiments. We're going to look at 2 methods of obtaining binomial probabilities in these lecture notes. The first one, we're going to look at the binomial probability distribution. Formula. And And then, after looking at the binomial probability distribution formula, which is a really long name, we're going to look at a table of binomial probabilities. Example 2. According to the American Red Cross, 7% of people in the United States have a blood type O negative. A simple random sample of size 4 is obtained, and the number of people, X, with blood type O negative is recorded. Construct a probability distribution for the random variable X. So first thing we want to do is construct a tree diagram to list the possible outcomes of the experiment. So this is a binomial experiment, and we have n equals 4 trials. So what is our probability of success? So P is going to equal 0.07, or 7%. And then what else do we need? We need our X values. So probability of success X is going to equal 0, 1, 2, 3, and 4. All right, so now we're going to go ahead and start to do our tree diagram. So let's see. For the first trial, what are our options in the first time we pick someone? Well, it's either going to be a success that they have O negative blood type, or it will be a failure that they don't. Now, for the second trial, we have 2 options for each one again. For the second trial, we could have a success or a failure. And then for the other time, we could also once again have a success or a failure from the first failure. We go ahead and color code these a little bit. So success will go with green, failure will go with red. So we can follow the path of success or failure. All right, so second trial. So let's go on to the third trial. We have multiple more options. So from the second success, we could go on to another success, or we could go to a failure. Same thing for the other failure. We could have a success the third time, or a failure the third time. Now, for this one, we could either once again have a success, or we could have a failure. And for the last one, we could have a success or another failure. So if you follow the very bottom one, if this path happened, we would have had a failure 3 times. Or we could follow the other path and say we have a failure, and a success. So there are many options for how this could go. And we're just mapping them all out. All right, we have one more trial to do. The fourth trial. So from the first, or not the first success, well, the first line of success, we could get another success or a failure. From this failure, we could either get another success or another failure. And then from this success, we could get a success or a failure, running out of room. From this failure, we could get a success or a failure. And then from this success, we could get a success or a failure. From this one, we could also get, really running out of room, a success or a failure. Last one, we could get a success or a failure. And very last, success or failure. A little harder to follow these because the spacing was not perfect, but it'll do as long as you can follow the arrows. And then color coding the failures in. Sorry if red's your favorite color. It's not always a failure color. All right. What are the number of successes? So let's see. Well, what are the outcomes? First off, let's list those. We'll just list those by S and F. So for the first one, we have SSSS. So 1, 2, 3, 4. Second one, we have 1, 2, 3, 4. So SSF. Then the other one we have SS. Okay, we did that one already. FS. So SSFS. And then follow the path a little differently. SSFF. let's see, the next one. SFSS. And then lastly, not lastly, but next one, SFSF. Okay, so just slowly going along and calculating them all out. Go ahead and try to write the rest of these out. Check in with me in a second. I'll write the rest of them down as well. All right, so I went ahead and wrote down all the different possibility or the outcomes, the different orders. So for the first time, all were successes. The last time, all were failures, and every possible outcome in between. So now what we're going to do is write down the number of successes, x. Let me actually move that up a little higher because that's crouching upon my answer. Number of successes. Okay, so the first one, how many successes do we have? We have 4. The second one, we have 3 successes, sorry. Third one, we have 3 as well. Fourth, we have 2. 3, 2, 2. I'm going to go ahead and just highlight all of the S values so you can see how many there are. We're aiming for the S's because those are the success, which we're trying to count. Let's write those down. So then 2, 2, 1, 3, 2, 2, 1, 2, 1, 1. And lastly, 0. Now let's compute the probabilities for each possible value of the random variable x. Okay, so to do that, we're going to go ahead and we want to fill out this table for the probabilities, which would be our x values. And our x values, what are the possible x values we had? Remember, 0 people would have O negative, 1 person could, 2, 3, or 4 people could. So these are the possibilities of our binomial probability. And we want to find p of x, so the probability of x for each of these values. So for p of 0, how would we compute the probability that 0 people have this? Well, the probability that 0 people have this is going to be this one right here. Let me use a different color. Or FFF. So how do we compute that probability? Probability of failure times failure times failure times failure. Well, that is going to actually equal the probability of f times the probability of f times the probability of f times the probability of f. And remember, the probability of failure, well, success was 0.07. So then the probability of failure would be 1 minus 0.07, which is 0.93. And we have that how many times? 1, 2, 3, 4 times. So 0.93 to the 4th power, which will come out to approximately 0.74805. So 0.74805. So that's the p of 0. Now let's find the probability of 1. So the probability of 1, how many different options do we have there? Well, that would be the probability of, let's go back and check our chart for the probability of 1. We have here, 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 and here. So those are these different probabilities. I'm going to go ahead and copy those down. So the times we got 1 for our answers was either SFFF or FSFF or FSFF or FFFS. As you can see, this is getting bigger. So now let's see. Notice we have the word or going on, which means we're going to have to use the addition rule for disjoint events. So which means that'll be the probability of SFFF plus the probability of FSFF plus the probability of FFSF plus the probability of FFFS. Now each of these come out to being written as, I'm just going to show it to you like this, and then I'm going to erase it because I don't have enough space for all of this. But for example, this one would be written as probability of S times probability of F times the probability of F times the probability of F, which would be in shorthand, so the probability of success was 0.07, and the probability of failure was 0.93, 0.93, 0.93, which could be written as 0.07 times 0.93 to the 1, 2, 3 power. That is just this one. That's what it equals. So for the sake of space, I'm not going to write all the rest of them out for you, but that is basically what's happening for all of them. You're just going to write out all of the multiplications for each of them and then find those probabilities. This is definitely a lot of work by hand. Okay. So I wouldn't expect you to do that middle part that I just erased. Easier way is to just think of probability of success times 3 of the failure. So that would be success is 0.07 times 3 of the failures, which is 0.93 to the third power. In this one, we have success once and failures 3 times again. And notice for all of them, it'll be the exact same thing. Oops. So how many of these do we have? We have 1, 2, 3, 4 0.7s times 0.93 to the third power. So I can shorthand write this as 4 times 0.07 times 0.93 to the third power. Now putting that into a calculator, we'll get p to the 1 equals 0.22522, approximately. So 0.22522. Next, we'll go ahead and look at P of 2, so the probability of the second one. Okay, let's go back and see which ones have 2s. 1, 2, 3, 4, 5, 6 of them have 2s. 1, 2, 3, 4, 5, 6 different options. So we're going to go ahead and write down those 6 different options for the 2s. And what are the 6 different options? So that's the probability of SSFF or or SFSF or SFFS or SSFF or FSFS or the FFSS. Okay, so this probability is actually gone over in the book if you want to check that out. I'm going to go ahead and skip to P of 3 since they don't actually do that in the textbook. But we won't have enough space to do P of 4, so if you want to try P of 4 by yourself and check the answer with the textbook, you can go ahead and do that. So let's take a look at the probabilities of getting a 3. So the probability of getting a 3, what do we have? We have this one, and lastly, that one. So only 4 different times we can end up with a 3. So let's go ahead and write those down. All right, so taking that back, so P of 3 is going to be the probability of getting an SSSF or an SSFS or an SFSS or lastly an FSSS. Okay, so once again, we have the ORs going on, so that's going to be the addition rule for disjoint events. So we can go ahead and write that out with the additions in place of the pluses. And once again, remember, these would be written out as the multiplication of each of the individual values. So I'm just going to write out the first one so we can see that again. And probability of success is 0.07. And how many times do we have that? 1, 2, 3 times. So that'd be to the third power. And then the probability of failure, which was 0.93. So that would be for the first one. But I'm not going to do that for all of them, and you wouldn't have to do that on the exam either. That is a lot of work. So just the steps that I show, make sure to show those on your exam. All right, so this would be, let's see, how many S's do we have? We have 3. So successes, 3 times the failure, 0.93, plus, and notice that's going to be the same for all of them. We have 3 successes and 1 failure. which is why the success is to the third power and the failure is just to the 1 power. And then how many of these do we have? We have 1, 2, 3, 4 of them. So we have 4 times 0.07, the third power times 0.93. And that comes out to be approximately 0.00128. Okay, so P of 3. All right, so filling these out, well, P of 3 we found together, which was 0.00128. The book gives us probability of 4, which you could go ahead and try by yourself to see if you get it correct. And then also the book goes over probability of 2, which is 0.02543. A lot of work by hand. I would not expect you to do all of this by hand on an exam, but I might have you do a problem that's slightly shorter than this. Maybe only 3 of these values or something like that, because it is a lot of work, a lot of hand and number crunching. Now let's take a look at the binomial probability distribution function. So the probability of obtaining X successes in N independent trials of a binomial experiment is given by the formula. P of X, so the probability of X is, so you have a combination and choose X, times our probability to the X power, times 1 minus P, times N minus X. So X equals 0, 1, 2, and so on. So notice, how did we get this formula? Well, it looks an awful lot like what we were doing here. What we did was, see right here, this is our probability to the X power. So let's take a look at this. Let's look at P of 3. This is our X value, and so we had our probability of success to the X power, 3, 3, and success, let's say success is red, times the probability of failure. Actually, I'll do, oh no, wait, let's take this back. Let's do X in yellow, and how about success in green, and failure in red. And then we have our failure right here, and we take our N value and subtract X from it. So what is our N value? In our problem, N was 4. So 4 minus our X value of 3 would give us 1, which is why we have that to the 1 power. So that's sort of a small way of letting you know how we end up with our formula, kind of giving you a hint on where it comes from. All right, so real quick, let's look at math symbols and the phrases in English. More than likely you know these phrases in English, but let's just go ahead and cover them again. So for the math symbol, this one is considered the following different options. At least. Another one would be no less than. Or lastly, we would have greater than or equal to. This is the most commonly used phrase for that. Now the next symbol we have either greater than or maybe more than. Now the next one we would have either less than or maybe fewer than. And the other one, you would have either, let's see, no more than, at most, or less than or equal to. And lastly, the equal sign, either exactly, equal, which is our common one, or is. Okay, so anytime you see these words in a word problem, remember which symbol they lead to. All right, so let's take a look at example 3. According to Statista.com, about 22% of all Hawaii households were wireless-only households, which means they didn't have a landline, from January 2007 to June 2010. In a random sample of 20 households, what is the probability that exactly 5 are wireless only? So what we're looking for here is the probability of exactly 5. Well, using our formula, what we want is, where's our formula again? we need to find out the number, the sample we're taking, the probability of success, and the probability of failure. So let's take a look at that. Well, what is our n value going to be? N is going to be the sample size, which was 20. What we're trying to find here for this problem is x equal to 5. And then our probability of success is going to be 0.22. Okay, so filling out the formula, we need C, so we have 20, choose 5, and then our probability of success, which is 0.22 to the 5th power, times 1 minus our probability of success to the n minus x power, which is going to be 20 minus 5. Let's simplify this a little bit. So that's going to be 20 minus 5. And then we have 0.22 to the 5th power. And 1 minus 0.22 is going to be 0.782. And the 20 minus 5th, 15th power. All right, go ahead. Let's plug that into our calculator and see what we get. This is going to be approximately 0.1922. So how would we interpret this? Well, once again, for the interpret, I always like to put it over a fraction. So I'll round this out to about 0.19, which would be about 19 over 100. So what this is saying is that if we surveyed 20 households 100 different times, we would expect to find about 19 of our trials to result in 5 houses that are wireless only. Bit complicated on the interpretation, but I always find it helps to write it out as a fraction. So now let's take a look at B. Fewer than 2 are wireless only. So what fewer means is, or fewer than, would be less than, right? So that's less than. So we want the probability of, let's see, our values, right? So our probabilities of what we find, so capital X, we want it to be less than 2. Well, what does this mean? The only options we have are, it's going to be either 0 or 1 or 2. So we have the or, so once again, that's going to be the addition rule for disjoint events, which is going to be P of 0 plus the probability of 1 plus the probability of 2. And each of these we're going to end up writing out like the above for the formula. So P of 0 is going to be 20, choose 0, times 0.22 to the 0 power, times 0.78 to the 20 minus 0, which is 20 power. So that was P of 0. Then we're going to do P of 1. That'll be 20, choose 1, times 0.22 to the 1 power, 0.78 to 20 minus 1, which is 19. And lastly, we'll add in C, 20, choose 2, because we're using 2 for x, and then 0.22 to the 2nd power, and lastly 0.78 to the 20 minus 2, which is 18. Okay, so what are all of these values going to be? This is going to be 20 factorial all over 0 factorial times 20 factorial, 0.22 to the 0, which would actually just be 1, 0.78 to the 20, plus 20 factorial all over 1 factorial times 19 factorial, times 0.22, 0.78 to the 19th, plus 20 factorial all over 2 factorial times 18 factorial, all over, 0.22 to the 2nd power, 0.78 to the 18th power. I'll go ahead and plug those into my calculators and see what I get. So after plugging this all in, I got that the probability of x being less than 2 is about 0.15. So once again, if I was trying to interpret this, once again, I label my side work, that's about 0.15, which is about 15 over 100. So what this is saying is if I surveyed 20 households 100 different times, we would expect about 15 trials to result in households less than 2 that are wireless only. Now let's take a look at least 2 are wireless only. Okay, so this is the exact opposite. That means the smallest amount of them are wireless. Or the smallest amount of them are wireless only, which would be the probability that x is actually greater than or equal to 2. So if I was to do x greater than or equal to 2, that would mean that I would need to compute all the probabilities up to 20. So 2, 3, 4, 5, 6, 7, 8, 9. Okay, that's looking horrible. I would have to do that huge formula for every single one of these values. I really don't want to do that. So once things start getting really big like this, a certain concept should come to mind. And that would be the complement rule. So this is going to be 1 minus the probability of the exact opposite, which is x less than 2. And what do you know? We already found that right there. So that would be 1 minus 0.15109. And that comes out to about 0.8489. So the probability of x being greater than or equal to 2 is right there. And once again, if I wanted to interpret this, I would go ahead and round this out to about, let's say it looks like 85 out of 100. So what is this saying? Well, in about 100 trials of this study, each time we pick 20 households 100 times, we would expect about 85 of them to result in more than or equal to 2 of the households having or being wireless only. Okay, so if we picked 20 households 100 times, we would expect 85 of those trials to result in at least 2 being wireless only. So because I have space for this one, I'll go ahead and write out the interpretation, even though I wasn't asked to. So in 100 trials of this study, we would expect 85 of the trials picking 20 houses each trial to result in at least 2 wireless only households. Period. All right, so now for D, the number of households that are wireless only is between 5 and 7 inclusive. So what is this talking about now? Between 5 and 7. So what numbers are between 5 and 7? And we're inclusive, which means we're including 5 and 7. Well, those numbers are just 5, 6, and 7. So what we're trying to find is the probability of our x value being between 5 and 7, and it's allowed to equal 5 and 7, which is also another way we could write it as 5 or 6 or 7. And then using the addition rule for disjoint events, we break this up into the additions. Oops, not or, it's addition now. And then we're going to have to write out the formula for each one of these. So P of 5 is going to be 20, choose 5, times the probability of success, which is 0.22 to the 5th power, and then the probability of failure to the 20 minus 5, so 15. Let's do it for 6. So for 6, we're doing 20, choose 6, 0.22 to the 6th power, and then 0.78 to the 20 minus 6, which is going to be 14. Lastly, let's do P of 7. So P of 7 is going to be 20, choose 7, 0.22 to the 7th power, and then 0.78 to the 20 minus 7, which is going to be 13. Okay, so I went ahead and calculated out these values, and then I get these decimals. So now lastly, I'll go ahead and find the probability of 5 less than or equal to x less than or equal to 7. And that comes out to 0.4043. All right, there we go, unboxing our answer. So once again, if you wanted to interpret this, that would be about 40 over 100. So in 100 trials, about 40 of those trials would result in between 5 and 7 of the households being wireless only. So next, we're going to look at obtaining probabilities from tables. So another method for obtaining probabilities is the binomial probability table, which would be in your book. So Table 3 in Appendix A, which is in the back of your book, or it's also provided on Pearson during the homework problems, this gives the probabilities for binomial random variable x taking on specific value. Table 4 in Appendix A gives cumulative probabilities for a binomial random variable x. Okay, so example 4 is actually optional. So if you want to go ahead, you can fill this one out by yourself, but our book does not actually require us to do this one. So if you want to, this is optional. What you would do is you can follow in the book. It's pretty simple. And how it explains, you just look at the table and you follow the column and the row to find your answer. So you can look in the book for this example, or you could email me to ask about this. And you can look at example 5 in the textbook as well on how to compute these using technology. Or as always, send me an email and we can set up a Google Meet time to go over some of the questions. So let's look at objective 3. Compute the mean and standard deviation of a binomial random variable. So we have the mean, or once again, we're now calling it the expected value, and standard deviation of a random or binomial random variable. All right. So a binomial experiment with n independent trials and a probability of success p has a mean and standard deviation given by the following. So the mean of capital X is going to be n times p. So your number of trials times p. Then we have our standard deviation of capital X is going to equal the square root of our number of trials times the probability of success, 1 minus the probability of success. So this would actually be the probability of failure, if you want to think of it that way. So now let's take a look at example 6. According to Statista.com, 22% of all Hawaii households were wireless-only households, no landline, from January 2007 to June 2010. In a random sample of 250 households, okay, so the sample size has gotten bigger, determine the mean and standard deviation number of wireless-only households. All right, so we're just going to go ahead and use these formulas. So mean of x is going to equal n times p. All right, let's find those values. So n is going to be our number of trials, which is 250. P is going to be probability of success, which is 0.22. So n times p is going to equal 250 times 0.22. And voila, we get 55. So the mean of x is 55. Now let's find the standard deviation. So standard deviation of x is going to equal the square root of, so my n value is 250 times my p-value, which is 0.22, times 1 minus my p-value, so 1 minus 0.22. This is going to equal, well, we already know what n times p is, that's 55. And then 1 minus 0.22 is 0.73, which we found a little earlier. Let me go ahead and shorten this radical because that's a little too long. And then, okay, let's see. So 55 times 73. 55 times 0.73 is 40.15. So 40.15. And we still have the square root of that. So what is the square root of 40.15? Ooh, we end up with, let me take away that equal sign, approximately 6.33. And as you remember on the exams or during your homework, it'll tell you where to round to. So that is my standard deviation of capital X. All right. Yeah, that was it for this problem? Yep, okay, just the mean and standard deviation. Now, for objective 4, graph a binomial probability distribution. So for example 7, we're given our table of values here, and we're told to graph a binomial probability distribution with n equal to 10 and p equal to 0.2. So probability of success, 0.2. Comment on the shape of the distribution. Okay, so we have this labeled for all of our values, but we don't have this labeled. So looking at all of our values here, what looks like the best way to label these? Well, the highest value I see is 0.3. So I'll go to around there. So let's label this 0.05, 0.10, 0.15, 0.20, 0.25, and then 0.30, and lastly 0.35. Now, for graphing these, what do we have? 0.10 for 0. So that's about here. So let me pick, I'll do red pen. It's about there. And I'll go ahead and say approximate values for when I write out it. So it's going to be 0, 0.10. Then for 1, we go about to 26, 0.26. So about there. So that'll be 1, 0.26 approximately. And then 2 goes about to 30. So let's see. 2, 0.30 approximately. And then 3, 0.20. 0.20. About there. Okay, I'm going to go ahead and pause the video and graph the rest of these. Go ahead and graph them as well and check your answers with me in a sec. Okay, so that's about the approximate values for all of them. Once again, note I did approximate values. I'll write for coordinates. All right, so what does this kind of look like? Notice, it's kind of, our data goes up, but then it kind of skews off to which direction? To the right. So this looks like it's kind of skewed right. Oops, skewed right. So notice the values for skewed right and left are starting to come back. Now let's go ahead and graph this. So I will label this like I labeled previously. We'll go in 5. So 0.10, 0.15, 0.20, oops, I don't know why I did that twice. 0.25 and 0.35. Okay, I'm going to pause the video. Go ahead and try to graph this by yourself and check your answers with me again. As usual, I'm just rounding off to about the 100th place for these values for when graphing. Okay, so graphing all of these values, once again, I approximated them and I wrote their values out. So approximate Now let's take a look at the shape of this graph. It looks pretty symmetric and bell-shaped. So we would say bell-shaped, symmetric. Okay, now let's take a look at the last of the graphs. You probably have an idea of what this one's going to end up looking like when we graph it. Once again, I'll pause the video. Go ahead and graph these by yourself and check your answers in with me a sec. Actually, right before that, I'm going to label this exactly like how I labeled it for the other ones as well, going in 5s. All right, so I went ahead and I graphed these out with the approximate values rounded to the 100th place. And what shape does it look like it's creating here? Well, here it's looking like it's skewed left. So our answer would be skewed left. All right, so a conclusion. For a fixed p, which is, remember, the fixed probability, as the number of trials, n, in a binomial experiment increases, the probability distribution of the random variable x becomes bell-shaped. Okay, so the more trials we get, the more likely it's going to end up looking bell-shaped. As a rule of thumb, if we have this, so n times p, so the number of trials times their probability, times 1 minus p, so times probability of failure, if this is greater than or equal to 10, then the probability distribution will be approximately bell-shaped. So this is very good to keep in mind. Why is this good? Why do we care if it's bell-shaped? Well, this result means that we can use the empirical rule to identify unusual observations in our binomial experiment. Okay, because remember, for the empirical rule, we could only use this on bell-shaped items. And remember, let's real quick. So the empirical rule was talking about number of standard deviations away and area associated with those. So if you went 1 standard deviation away, you would get 68% of the data. If you went 2 standard deviations away, remember, you would get 95% of the data. And if you went 3 standard deviations away, you would get 99.7% of the data. Okay, so that's what the empirical rule kind of went over for us. And one of those problems was on the exam. That's one of my favorite kind of problems. So recall that the empirical rule states that 95% of all observations on a bell-shaped curve lie within 2 standard deviations of the mean. That is mu minus 2 and mu plus 2 times your standard deviation. So the values lie between these two numbers. Any observation outside of this interval may be considered unusual because the observation occurs less than 5% of the time. Oops, squeezing that in. How do we know it occurs less than 5% of the time? Well, we're looking at 95%. And 100 minus 95 would give us that 5%. So anything that falls outside of the 95% would be less than 5%. Okay, so that's why it's useful to know if we can use the empirical rule, because then we can easily find any unusual observations. So now let's take a look at example 8. According to Statista.com, 22% of all Hawaiian households were wireless-only households, which means they have no landline, from January 2007 to June 2010. In a random sample of 250 households, 175 were wireless only. Is this result unusual? Okay, so let's see. Can we use the empirical rule to determine if it's unusual? How do we know if we can use the empirical rule? Well, we had that one thing that we said, if n times p, 1 minus p, is greater than or equal to 10, then we can say that our observation is approximately bell-shaped, which means we can then use the empirical rule. So let's check that first. So n, what is n? N equals 250 households, and p, our probability, is 0.22. So checking that, so 250 times 0.22, then 1 minus 0.22. Is this greater than or equal to 10? And notice, when I'm not certain, I put the question mark. I wouldn't not include the question mark, because then maybe I'm stating something incorrect. So I'm going to go ahead and include our question mark because we're not certain this is true. So let's calculate this out. 250 times 0.22 times 0.8 greater than or equal to 10. And we get 42.9, which is greater than or equal to 10. So yes. So because NP times 1 minus P is greater than or equal to 10, we can use the empirical rule. All right. How do we use the empirical rule? Well, so for the empirical rule, we're going to use the 95%. And so we're going to calculate the boundaries for this, which was mu minus 2 times the standard deviation. That would give me my lower bound. And then my upper bound would be mu plus 2 times my standard deviation. Okay, so an image on what I'm looking at. Ew, that's an ugly curve. So an image, I am looking at this. So this would be mu minus 2 and then u plus 2 times my standard deviation. So calculating this out, what is my mu? Well, we calculated this way back in example 6. So the mu that we found was 55 minus 2 times our standard deviation, which was 6.33. And we'll end up with 42.34. So that is my lower bound, 42.34. Now my upper bound is going to be mu plus 2 times sigma. So 55 plus 2 times 6.33. Oops, let's calculate that out. That 3 is not looking nice. Okay. 67.66. So anything that falls outside of these would be considered unusual, because those would be falling outside of the 95%, or those would be falling within the 5% total. So what was my observation? I was looking at 175 were wireless only. Where does that value fall? Well, that one falls all the way out here. That's 175, somewhere out there. That is definitely outside of what would we consider the normal range, because it falls in the 5%. So our answer would be, and I'm totally running out of space here with my diagram. The answer would be, what would the answer be? So since 175 is greater than 2 standard deviations away from our mean, it is an unusual result. Period. So what would be considered a usual result? Well, anything in between 42.34 and 67.66 would be considered a usual result. For example, 50 would be considered usual, or maybe 40. Okay, but 39 would also be considered unusual because that would fall below. Okay, all right, so that's a good and useful reason to use the empirical rule, and that, I believe, is it. Yeah, that is it for our lecture notes. Please email me if you have any questions.